Howdy, this is a video on first-order predicate logic based on the textbook by Suppes Hill. We're dealing with two or more universal quantifiers. The next video, by the way, will cover both universal quantifiers and existential quantifiers. It's a little bit tricky, but with several translation examples, it's not too bad. With multiple quantifiers and multiple variables, we can deal with the relations between different classes of things. Now, this video presentation returns us to the Suppes Hill textbook. In particular, we're dealing with pages 223 to 230. Now recall that a one-placed predicate allows us to assign an attribute to an individual. For example, Socrates is a man, where man, of course, is the predicate. We give the predicate an uppercase letter, capital letter, such as capital M for man, and our individual, our subject, that which the predicate is about, namely Socrates, we give that a lowercase letter, such as s, lowercase s. In example 2, we have Socrates is a poor man. Here, it's still best to think of this in terms of one-placed predicates. So we're going to symbolize this with a conjunction. So we'll take the predicate poor, we'll take the predicate man, make a conjunction, so we have capital M, lowercase s, for Socrates is a man, and capital P, lowercase s, Socrates is poor. All right. Now, relations are possible with constants. We can have a relational predicate. And here, straightforwardly enough, capital letters represent relations, just like our basic properties or our predicates, so to speak, and lowercase letters represent individuals. Example 1 from the textbook, Elizabeth II is the mother of Prince Charles. So the relation is mother, and thus we will give that a capital letter, such as M. We have two individuals. We have Elizabeth II, we'll give that lowercase e, and we have Prince Charles, we'll give that a lowercase c. And so we have Elizabeth II is the mother of Prince Charles. Note that the order matters. So this is not the same thing as capital M, lowercase c, lowercase e, because this would tell us that Prince Charles is the mother of Elizabeth II, and that's simply not the case. Motherhood, we might say, is non-symmetrical. So from the fact that Elizabeth II is the mother of Prince Charles, it does not follow that Prince Charles is the mother of Elizabeth II. Or how about this? Wilbur and Orville are brothers. So we have another relational situation here. We can give capital B for brothers, lowercase w for Wilbur, and lowercase o for Orville. In this case, parenthetically, the order doesn't matter because brothers is a symmetrical relation. So because Wilbur is a brother of Orville, it follows that Orville is the brother of Wilbur. We just know that by the content. We know that by the meaning behind those statements, those propositions. How about this potential example? Wilbur and Orville are men. Well, there's no relation there. Rather, it seems we're back at a one-place predicate. So I think it's best to translate that as a conjunction. So we'll say capital M for men or man, lowercase w for Wilbur. So Wilbur is a man, and we have Orville is a man. And as I said, order is important. So let's say we have Joe is taller than Mike. We can say capital T, lowercase j, lowercase m. That works because we're saying Joe is taller than Mike, whereas the second possibility, capital T, lowercase m, lowercase j, this one's saying Mike is taller than Joe, and that is not the case. And also recall we can quantify classes of things. Turns out we can have relations with variables. And this is pretty cool, actually. Here's two potential examples. Dogs hate cats. That is a good example because, of course, dogs is a class of things. Cats is a class of things. And we do have a relation, namely hate. The second example, obviously, is not about classes of things because we are talking about individual persons. Okay, sorry for the interruption. So that happens when you do this when you're recording. So Joe obviously is a particular person. Mike's a particular person. They're not classes of things. Okay. And for this, of course, this example that Joe hates Mike, we'll just say capital H for relation of hates, lowercase j for Joe, and lowercase m for Mike. But we'll need quantified variables for dogs hate cats. We'll need two quantified variables. We give two classes of things. Here's a kind of funny example. The Sears Tower is taller than everything that exists. It really is a funny example, and maybe I shouldn't have included that because, strictly speaking, we need to introduce the notion of identity to get a good translation of that. So the Sears Tower obviously is a particular thing, right, in Chicago, and everything that exists that is going to be a variable. But if we give something like this in terms of our symbolism, we'll say something like for all x, let's say capital T for taller, and then we'll say lowercase s for the Sears Tower, and then x for everything. That's, strictly speaking, not a good translation because that's saying for all x, the Sears Tower is taller than everything, but x can include the Sears Tower, interestingly enough. So that would be saying the Sears Tower is taller than the Sears Tower? That doesn't really make sense. So we really have to modify this, and we have to specify that x cannot be the Sears Tower to make that a better translation. And obviously the Sears Tower is taller than everything that exists. That's not a true statement. But at any rate, it's kind of an interesting example, although an odd one. To be sure, our propositions have become somewhat more complicated, somewhat more nuanced, but they still nevertheless maintain the same general forms. If we think about universal affirmative propositions, such as all A's are B's, or the universal negative proposition, no A's are B's, those two basic patterns, at least for universal statements, still show up here. So all A's are B's, we have for all x, if x is an A, then x is a B, and then for no A's or B's, we have for all x, if x is an A, then it's not the case that x is a B. So for example, Socrates knows all people. That really is of the general form, all A's are B's. So you're going to have some antecedent, some consequent. So Socrates knows all people, and we can think about our general hints I give here. So find what needs a quantified variable. Are we talking about everything of something or some of something? Find the relations. So we have Socrates knows all people. All people, that definitely needs a quantified variable. We have a relational predicate, knows, and Socrates, of course, is an individual person. So we can get that into predicate logic. For all x, if x is a person, then Socrates knows x. So we have, for all x, let me try another color there, actually. So let me try this. And this is just regular yellow. For all x, if x is a person, then Socrates knows x. And it's of that all A's are B's form. Or how about dogs hate cats? Well, there, we're thinking of it in terms of all dogs hating all cats. So we need two quantified variables. And our relation is hate. So that is our relational predicate. So we'll say that for all x, for all y, if x is a dog and y is a cat, that's the antecedent, then capital H, lowercase x, lowercase y. Because we have for all x, for all y, if x is a dog and y is a cat, then x hates y. How about that somewhat strange example, the Sears Tower is taller than everything? I'm going to modify that actually a little bit. Instead of saying than everything, let's just say than any building. It's not a true statement, but we can still work with it. The Sears Tower is taller than any building in Chicago, at least. So I think it's in Chicago is the Sears Tower, and then the second tallest is a Trump building, and I think 3 and 4 have recently changed. So I think there's a new third tallest building. So before it would be the AN building, then the John Hancock building, but I think those have changed a little bit. But in any case, the Sears Tower is taller than any building. But here I'm going to have to introduce a notion of identity to make this work, because we don't want to say the Sears Tower is taller than the Sears Tower. But in general, of course, if you look at that proposition, taller than is a relation, the Sears Tower is a particular building, particular thing, and then we have this general class of things, any building. So I'm going to first state that the Sears Tower is a building, so we can say capital B, lowercase s. So the Sears Tower is a building, and for all x, if x is a building and x is not the Sears Tower, so we have a denial of identity there, then capital T, lowercase s, lowercase x. The Sears Tower is taller than x. So we have the Sears Tower is a building, and for all x, if x is a building and x is not the Sears Tower, then the Sears Tower is taller than x. Or how about everything is taller than the Sears Tower? And this time I'm not going to say any building is taller. Let's just say everything is taller than the Sears Tower. It's a strange example. It's obviously a false statement, but we can still work with it. So in this case, we can get the following. For all x, if x is not the Sears Tower, then capital T, lowercase s, lowercase x, lowercase s. So the order matters because we're saying x is taller than the Sears Tower. So for all x, if x is not the Sears Tower, then x is taller than the Sears Tower. How about every man is older than any boy? So again, notice what needs quantification. So we have this every, this any. So we definitely need two quantified variables. We have this relational predicate about older than. And so we can get the following. For all x, for all y, if x is a man and y is a boy, then we have x is older than y. So for all x, for all y, again, it's of that all A or B form. So we have this antecedent, we have this consequence. So if x is a man and y is a boy, then x is older than y. How about everything loves everything? In this case, I'm thinking in a very general sense. Literally, everything loves everything, not just people love people or something like that. And this is a classic example you'll find in a lot of textbooks, something like everything loves everything. So we need two quantified variables because we have an everything and another everything. So we have for all x, for all y, lxy. So for all x, for all y, x loves y. Everything loves everything. So we can think of everything there is x, everything there is y. So it's not too bad. But there's some more complicated examples, at least a couple of them. I think like 6 is pretty interesting. 7 is pretty interesting from the textbook. Let's start with the first one. Jim teases Francis. So here we have no quantified variables. We have two particular people. We have a relational predicate, teases. So this is pretty clear cut. So we'll say capital T for a relational predicate, and then we have our two individuals, lowercase j, lowercase f. And of course, order matters there. All things attract each other. Well, that's pretty much like everything loves everything in terms of its general form, its general structure. So we have for all x, for all y, capital A, lowercase x, lowercase y. So for all x, for all y, x attracts y. All things attract each other. How about number 6? It's a little bit more interesting. Brothers sometimes quarrel with each other. All right. So we have quarrel with each other. That's definitely a relational predicate, but even brothers we can treat as a relational predicate here, or as a two-place predicate. Because we can say the following. All right, for all x, for all y, if capital B, lowercase x, lowercase y, then capital Q, lowercase x, lowercase y. Because look, we have for all x, for all y, if x is a brother of y, then x quarrels with y. So we have two-place predicates. We have this two-place predicate here, the antecedent, and in the consequent. And we have those two variables, x and y. How about any boy who wants to play with the volleyball must first pump it up? Okay, so this one's also a little bit different. It's kind of interesting. It's kind of tricky, I think. So we have wants to play. Well, first off, note wants to play. So we have a boy who wants to play with the volleyball. We also have this pumps it up. So the boy must pump up the ball. So we have one quantified variable, but let's be careful here. We're going to have two-placed predicates. So let's think about this. So for all x, so what would be the antecedent? So first off, that x is a boy. So capital B, lowercase x. And now let's think about x wants to play with the ball. So we can say capital W and then lowercase x, lowercase b. So any boy wants to play with the volleyball. The volleyball will give a lowercase b. The capital B is for the boy. So that's the antecedent. And then the consequent is x must pump up the ball. So it'll be capital P, lowercase x, lowercase b. So for all x, so in the antecedent we have if x is a boy and x wants to play with that ball, then x must pump up that ball. We have two relations, really. Wanting to play and pumping it up. All right, number 8. Earl helps Betty and is helped by Jennifer. So we have two relational predicates. Helps is helped by. We have these specific people, so no quantified variables. So we can get the following. So capital H, lowercase e, lowercase b. Earl helps Betty. We have a conjunction and is helped by Jennifer. Is helped by Jennifer. So Earl is helped by Jennifer. So capital H, lowercase j, lowercase e. So the order matters. The j comes before the e because it's Jennifer that's helping, or is helped by, right? So if it's helped by Jennifer, if Earl is helped by Jennifer, then that means Jennifer helps Earl. And finally, birds are afraid of cats. This is very similar to some of the other examples, like, I don't know, dogs hate cats, that kind of thing. So we can think about all birds are afraid of all cats, that kind of thing. So we need two quantified variables, and we get the following then. So for all x, for all y, if x is a bird and y is a cat, then x is afraid of y. So for all x, for all y, if x is a bird and y is a cat, then x is afraid of y. So they're actually not too bad. Keep in mind, of course, our general forms like all a's are b's, no a's are b's. I guess I should have given an example of no a's or b's here. But at any rate, but they can get tricky. So I think like number 6 and number 7 from the textbook from Suppes Hill, I think those are the more tricky ones there. So up next will be more of section 6.2 with arguments, with proofs.